The API gateway was one of the first decisions that we had made when going down this architecture. And we picked this pattern literally 2 days before Amazon launched their their API gateway product. And it turned out that that wasn't a big deal because what we wanted to do with it, Amazon's wasn't mature enough to do. We picked a product called Tyk, T-Y-K. It's a Golang-based open source product. And basically, what this API gateway does is handles all of your authentication. So it handles all your OAuth termination, it handles rate limits, it's configurable for APIs, it handles API versioning. So if you have a user API and you want to create a new version of that API, this is smart enough to figure out how to send your requests and how to manipulate your requests so that you can manage a public API that is different from your internal API. And so what we wound up this let us do was create an external REST API, which was available outside of our firewall, that was very slowly evolving, and it was unaware of anything that happened behind our firewall. And then on the inside, we had internal services that all were very fast iterating. They were very, we could ship them and change their APIs daily and use Tyk as that middle layer to glue them together. Worked phenomenally well. Would definitely recommend this pattern if you're going towards a service-oriented system. Use some sort of an API gateway. It really does simplify a lot of things. Zooming back out, the next layer I want to talk about is the back-end data bus. At this point in time, there were really two big players in queues, in messaging queues. There was a RabbitMQ and there was Kafka. Kafka was a nightmare to work with PHP. The PHP drivers didn't really exist well. It's not like today where it's pretty easy to work with Kafka from PHP. So we decided to go with RabbitMQ because of our needs and because of the PHP drivers. And basically what we did is we used this as an event source. So whenever you made a change to any one of the services, so the user domain changed, we would emit an event saying the user was created or the user changed or whatever, and then it would route that message both to a Amazon S3 bucket, so we had an archive of every change in the system, as well as to every other service in the application. So what this allowed us to do was decouple changes in the application, let different services listen to be able to update their states. One of the problems with this, though, that we learned as we went is although we had this archive of all of the messages that were ever sent, the application never used that archive. And so what was in the archive was actually slightly different than what was in production, which basically meant we had no actual single source of truth. And it wound up being incredibly painful. One of the big reasons is we had some bugs with the code that was emitting events, and so we had events that were wrong, so the archive didn't match the database. But also, RabbitMQ is a non-ordered queue, which means if you send two messages in sequence, one and then the other, they may be received out of order. And for our use case and what we were trying to do, we didn't realize that that was going to be a major problem. That is one thing that today, if you were going down this road, just use Kafka because it solves a lot of those problems for you. We use two different types of events. So I mentioned the state change event on top up here, where we would basically take whatever happened to the user table or to whatever object, send out an event, and anybody could listen to it. And we also used it for remote procedure calls. One of the things our application did was a lot of heavy video work. So we did a lot of video transcoding and stitching together video files dynamically. And so having services that just communicate through RabbitMQ, where I can say transcode this file, and then seconds or minutes later, I get another message back saying that file has been transcoded, was a key part of our architecture. And so we used this RPC system. And we had actual specifications for both of these, and we really put a lot of time thinking how to make this robust. And the final layer would be the actual services themselves. About 3/4 of the services were written in PHP. About 20% were written in Go, and we had a couple of Scala services as well. 3 rough types: a domain service, which if you're familiar with domain-driven design is kind of similar to either domain entity or a bounded context. They modeled the business entities and the business behavior. We had the async services, so I mentioned video transcode service, et cetera. And then we had these things that we called meta services. Let's actually take an example and describe that. So this is a rough diagram of our domain. You have users, assignments, lesson history, lessons, content, and assets. Don't really worry too much about what the definitions of each of them are, just we have relationships between these entities. And what we wound up doing is we made a service around each entity. And so we had a user service, we had a lesson history service, an assignment service, et cetera. And so the question comes, if we want to display an assignment to the user on the front end, how would you do that? Well, we could naively query the assignment service and then query the lesson service to get every lesson belonging to that assignment, and then query the content service for every single lesson, and you wind up with this gigantic explosion in queries where the front end would have to make maybe 1,000 requests to render one assignment. And so instead, what we did is we built a meta service. Now, this meta service knew about everything below it. It could subscribe to RabbitMQ to listen for changes. So it was smart enough to be able to assemble all of the things with either 0 calls or with very, very effective caching. And so when you make a request from the front end, instead of going to every individual service, it just went to this meta service. And the meta service knew how to route all the requests and how to assemble back the results. Now, you may be looking at this and saying, this kind of looks like GraphQL, or at least in concept what GraphQL does, and it's different. GraphQL does the assembly, but this meta service also had business logic. It wasn't just figuring out how to get the right properties from the right types together. It actually understood the meaning of them and could do things like permissioning. It could do things like time-based data, where we had a use case where we wanted the actual data to change depending upon the time of day, and this service actually understood all of those different constraints. So it was kind of like GraphQL, but it was a step above it, and it was more integrated into the business. But then there's another question. If we wanted to get a list of lessons by the user that authored them, how would you do that? It's kind of a nightmare. It took us about 1.5 years to figure out a really good scalable answer to that, and it wound up being Elasticsearch and a search service, which is kind of nasty. So I'm going to go through the infrastructure pretty quickly, because I know we're a little short on time today. We were using Mesos at the time, which Mesos is basically a job orchestration system. So you give it a bunch of servers and jobs, and it figures out how to manage those jobs across the servers. We did it because we were using Spark as our big data engine. But then we added in Marathon, which basically allowed us to run Docker on top of this cluster. So all of our compute was managed by one system, both for our big data systems as well as our production infrastructure. And what this basically meant was we have a cluster of servers, and we're running containers on some of them, and we're using load balancers to be able to direct traffic in. And so an actual external request would come in, bounce back and forth, hit our API gateway Tyke. Tyke knows to forward that to an internal service, which then goes through the internal requests and winds up in our internal service. This is a lot of network hops, but in practice, it was actually quite quick and incredibly reliable. We were actually averaging about 6 nines of uptime over about 1.5 years with this system. So it was really quite reliable, and the latency was not that bad. And then if service A wants to call a different service, let's say B, it would just go back through the internal ELB and call that other service. And so what this allowed us to do was have multiple versions of each container running live and using our Marathon to manage it all and just configure our ELBs or load balancers dynamically. And so it was really quite quick. We also did a lot of work on our logging infrastructure and our metrics, such that we used Logspout to aggregate all of our logs through Kafka into a service called Datadog, which does log analytics and metrics. We also used StatsD, if you're familiar with Etsy's project StatsD, to collect application metrics. And then finally, and this I think is a really interesting one, we spent a lot of time working on Zipkin. Zipkin is a distributed tracing tool. So basically what Zipkin does is it allows you to visualize a request to one service and see all of the other services it depends upon, and actually trace requests through multiple services and correlate them back together. I'd say this is probably one of the biggest mistakes that we made, is not prioritizing getting this up and running sooner. One of the biggest challenges to running a distributed system in general is visualizing what's happening. Zipkin is very good at doing that. I wish we would have gotten that integrated and built sooner, and it wound up being something that we turned on about a year into the project, which caused us a lot of pain. Finally, for our infrastructure, we defined and created a JSON definition. This described every single service. So in the root of each repository would be a service.json file, which had the name of the service, what other services needed, were its dependencies, what data stores were needed. So here, this is defining a Postgres database that this service depends upon. It could be a MySQL database. It could be Redis. It could be Memcache. You just describe what data stores it needs, and our automation would read that, figure out what it needed, and spin up and automatically populate credentials according to a convention. So this way, we were able to 100% automate the infrastructure based on these definition files. Does this look familiar? The last three slides where I talked about should feel pretty familiar if you've kept up with modern infrastructure. This is basically Kubernetes. When we started this project, Kubernetes was announced, but was not released yet. Today, don't do any of this. Don't waste any of your time on it. Just use Kubernetes. It doesn't mean you don't need to invest in automation. It means you don't need to invest in the infrastructure side. Do invest in the ops and do invest in the infrastructure, but just use Kubernetes. So local dev is a completely different story. The infrastructure I think we nailed. Local dev was perhaps one of our biggest screw-ups. We built a tool that would read these service definitions and spin up a Docker cluster with Docker Compose and actually get everything wired together. So if your service depended upon a different service, it was smart enough to figure out how to spin up that other service, get everything orchestrated, get everything working. It was really quite an amazing tool. Handled migrations for you, so as services evolved, it handled spinning all that up, and nobody used it. Instead, every engineer ran their own service individually on their laptops. If they needed another service as a dependency, sometimes they faked it, sometimes they mocked it, sometimes they just never actually tested it. Sometimes they would actually grab one of the other engineers and say, help me get the content service running on my machine, get it running once and then never update it again. So we were running on old versions. Absolute nightmare. Development environments were completely different from their production environments. If a developer needed a PECL extension, they would install it locally on their machine and then it wouldn't be available in production, and they would ship code and things would break and we'd not know why. Really a nightmare. And so we started and we stopped and we started to think about why. Why was it? And on the surface, it was slow, it was unreliable, it was difficult to use. When I say slow, it took about 15 minutes to build all the containers, get them all up and running, have them all like started and wired together correctly. So at the start of the day, it took you 15 minutes to start your local dev environment. That's a pretty bad experience. But we started to dig a little deeper, and what we realized was this is the excuse. This is not the reason. The reason was it was somebody else's problem. Local development in the environment and that tool was one developer, one of the managers on the team. It was his job to build and maintain that system. So when people had problems with it, it was, hey, Bill, go fix this thing, it's broken. And then they went off to do something else. There was no incentive for developers to own and really be responsible for their own local development systems. And hence, it rotted and caused us a ton of problems. So we spent about 2 months building the initial services, building the infrastructure, and getting everything ready. And then we get to the point where we're ready to try to turn this thing on. It took a month from the time we were code complete in the first set of services until we started accepting actual production traffic. Yeah, not good. You know, I mentioned environment differences where development was depending upon different extensions and were available in prod, and those took a couple days to sort out. But the biggest problems were we were never integrating each of these services early. We were integrating them into prod. So if there were bugs in APIs, those were coming out in production. And so it took quite a while because our feedback loops were very long. Developers had moved on to other projects by that point. And so by the time they had to debug and the infrastructure was ready for them to debug, it was a real pain in the neck for them to work with. So it took a very, very long time to actually get this thing up and running and up to speed. There's a lot here. I'm not going to go into all of these. You can read the slides afterwards if you're interested. But I think the biggest part was the deployments required a high level of coordination. And what I mean by that is most of the changes that we had to do only affected one service. And so those were easy to build and easy to roll out. But anytime a change had to affect more than one service, we now had to make many changes, get them distributed, get everything coordinated, and what would normally take an hour or maybe even 2 hours on a monolith wound up taking us a week to do in this type of a system. So it really became difficult. And so digging in on that a little bit, we had to respond to change. The product was changing, partly because we built the thing, we got it in front of clients, and they wanted something different, or they requested changes, or it was almost right but had a couple things that we needed to build. We had executives at the company who were, oh, you have to build this other feature and you really need this, and so you need to do that. Or, you know, there was a couple things about this that we really got wrong on the first couple iterations. And dealing with change is a natural part of software development. Problem was, we had this sort of a hierarchy. Now, it's important to note these aren't categories. Each one of these has actual business rules and business logic associated with them. Well, the business wanted us to add in another layer in here between topic and lesson that they were calling milestones that had a lot of logic associated with it. And they also wanted to get rid of this one thing down here. Now, in a monolithic application, how difficult would a refactor like this be? Probably pretty easy. You know, maybe an hour, maybe 2 hours of refactoring, a couple database migrations, and you're done. For our situation, we're sitting here with this, and how would you refactor that hierarchy? Well, first you've got to deploy, you got to figure out what the new schema is going to look at. Then you've got to deploy anything that depends upon that to be able to talk to either one. Then you've got to deploy the new service, and then you have to deploy, it took what would have taken about 2 hours on a monolith, wound up taking about 2 weeks here. It was really, really, really difficult. Simple ETLs turned into major coordinated surgery because we had to keep this thing up and prevent downtime. And so, kind of wrapping up a little bit here, a couple of the lessons that we learned. Service calls are unreliable. I don't think we appreciated this when we started. If I tell you a method call is reliable, or if I ask the question, how reliable is a method call? It's something you don't even think about. If you call a method on an object, what is the chance that you expect that method call to fail? I'm not saying that the method errors. I'm saying the actual call, that the object will not receive that method. 1 in a million chance of that? Probably, sorry, that's 1 in a billion. No, it's way more than that. It's way more than that. In practice, with PHP or any other object-oriented programming language, you don't think about it. A method call is, for all practical purposes, guaranteed to be received by an object. With network calls, when you're calling another service, your best case is about 1 in 100,000. So you're infinitely, literally infinitely less reliable. A service call is infinitely less reliable than a method call. So when we used object-oriented design patterns and object-oriented design techniques at a service layer, we backed ourselves into a major corner and caused ourselves a lot of trouble because of that. Services are less reliable than methods. Don't design them the same. And so it raises a really interesting question. How small should you build your services? We went an extreme. I think the thought that we used was you should be able to rewrite any of the services from scratch in less than 2 weeks. That's how big we were trying to define each one of those services. And that was not right. If you remember this diagram from before, what we should have done was that. Create a lesson service that took care of everything within that domain. The reason is it's easier to split apart a big service than it is to stitch 2 small services together. One of our developers, a friend of mine, Daniel Kuzno, coined a term, microliths for this case. If you're building a new service that you don't really understand well, make it really, really, really big. And as you understand it better and run into performance constraints, that's when you make it smaller. That's when you break it apart. And so the lessons that I learned and kind of what I want you to take away here is don't do microservices unless you have a dedicated team to tooling and automation. It's easy to manage a single monolith because there's not many moving parts. The second you have 10 services or 20 services or 50 services or 100 services, the number of moving parts and number of interactions increases exponentially, and you need tooling to help you with that. If you don't have that tooling, you will fail, guaranteed. Do not try services unless you have a dedicated team. Again, we just talked about this. Start with big services because it's easier to split apart something that's too big than it is to stitch together something that's small. Automate everything. Spin up, deployment, migrations, those are usually things that we talk about automating, but also automate your backups and state restoration. If you want to work on a bug locally and not in production, how do you get the system into a known state? How do you get the system to mirror a production state without having to download production data? It's a difficult problem, and if you try to automate it, that's, I think, honestly, the only way to try to solve that problem. Don't plan for failure, live it. We built happy paths first. We built the success case, We built the success case, and then figured out how could it fail. What I've started to do now, because I still use services, and I would still use services moving forward, but when I do, I start with how can this thing fail? And I write the code for those failures first. And I deal with those failures first. And then only once every failure I can possibly think of is handled, then do I worry about the success case. Because failure will happen, and it's going to happen more than you realize. Finally, and this is something I didn't really talk about here yet, but define your objectives for each service. The business doesn't care about requests per second. So if you look at a content service, the business they don't care at all if you're able to do 200 requests per second to that service. That doesn't mean anything to the business. But if you're able to say 50 pieces of content were rendered per second, that's meaningful to the business, right? 50 lessons delivered per minute is meaningful to the business. Define what success looks like for every service to the business, not to your tech. Track all those tech metrics because you're going to need those tech metrics to help debug and understand what's going on. but figure out what the business needs and why this thing exists for the business. And I think the biggest thing that I've learned, and services aside, I've started to come to the theory that complexity, I think, is our biggest job as software engineers and software developers, is managing complexity. We can move it around, we can offload complexity onto our tools, we can do a whole bunch of other things to complexity, but we can never eliminate it. We can only shuffle it off. And where you shuffle it and how you shuffle it and how you move complexity is going to vary depending upon your needs. It's way too easy to create a system that is so complicated that you can't possibly hope to understand it. And if you can't understand it, how can you maintain it? How can you run it? How can you actually deliver value with a system that you don't fundamentally understand? Thank you. Questions? What happened to the project? After I had left the team, they wound up continuing building out the team, launched it, got success, and to the point where the company was eventually bought out, and I don't know what happened from there. But they kept iterating. They solved a lot of the things that I identified here. They wound up fixing independently afterwards. So it wound up being a success in the long run, but the technology problems definitely caused issues along the way. Why did I leave? It had nothing to do with the technology. It had nothing to do with anything in this talk. There were other issues that caused me to leave. Other questions? Yeah.
What was the initial reason to move to microservices? So this is my first question.
Yep.
My second question is, you said that you planned like 6 months for this refactor, right? And how long did it take?
So question one was, I'm sorry. What was the reason for the architecture and microservices, and then what was the time versus how much it actually took? The reason that we chose microservices was bullshit. It was like the technical fetishism, I guess. It was the new hotness. We created a whole bunch of reasons that we used to justify it, to like call out that we did. You know, it's easier to defend. It's easier to respond to changes. But realistically, it was because we wanted to play with cool new technology. To be 100% honest. And then what was the timeline? We initially were looking at 3 months to get our MVP up and running and out the door. We had scheduled for 2 months, we booked on 2 months, and we launched the initial version exactly on that 3 month, on the day. March 31st of 2017, we actually went live with it, exactly on schedule. Where the primary slowdowns happened was afterwards, and with velocity towards changes beyond that. It took a lot of pain and a lot of blood, sweat, and tears to get that thing launched in 3 months, but we did hit the original date. Any other questions? Yeah. No, I would not have chosen to refactor the legacy system, but I also wouldn't have chosen to rebuild it, at least in the way that we did. I think it's a very, very tricky problem, and I do think that our initial assessment that we needed to build a second product was correct. I don't think we needed to build a full ground-up second product, though. I think we could have gone smarter and built a second product within the original and been very careful about keeping them separate so that we weren't really refactoring the old one to do the new things, but we were kind of migrating it as we went along. That's probably how I would have done it. So, all right, thank you. And if you want to come up, I got something for you. Thank you, everybody. Enjoy the rest of the conference.